people. So these people are considered different people and segmented in a different region, okay, as a different person. This is the second, and then the third one is panoptic segmentation, combined semantic and instant segmentation, providing comprehensive coverage by labeling all pixel in one image. Okay, here you can see it's combination of the semantic and also the instant segmentation, which you can see three people segmented differently. Okay, so in the traditional image segmentation, okay, there are several techniques, okay, in image segmentation, which use threshold method, region-based, age-based, watershed-based method, or clustering-based method. Okay, each have their own technique, okay, such as using the Otsu threshold, region growing, Kenny, watershed, and K-means. Okay, so these are the traditional one. So traditional thresholding is a simple method for segmenting images. It involves setting threshold to divide pixel into two classes, which is pixel with value greater than the threshold are set to 1, and which pixel with the value less than the threshold are set to 0. So this is basically when a picture, okay, where you can get the white and black picture of a threshold value. Okay. So next, in age segmentation, also known as age detection, refers to the process of identifying ages in images. From a segmentation-based perspective, age detection involves identifying which pixel in an image are considered age pixel and categorizing them as such. Okay, so you can see the age of the hand, the age of the face, the hair of this child. Okay, so this is basically the age, but obviously you cannot see the maybe the eye is not the age is not segmented properly, or the hand or the shirt, because the shirt there's a lot of line on the shirt. Okay, so these are some of the downfall of this technique. Okay, so what is the differences between the traditional versus the deep learning segmentation? The traditional technique overview, thresholding and age detection are foundational yet limited method typically used in image segmentation tasks. So the limitation of traditional method, this technique struggle with complex images and cannot handle variation or overlapping objects effectively. And so nowadays, deep learning is one of the way. Okay, one of the most prominent convolutional network like UNet and SegNet have revolutionized segmentation through superior handling of intricate visual data. So in deep learning segmentation, it used neural network to automatically segment images into meaningful region. So the features learn from large data set automatically extract features from images and improve accuracy and performance over traditional segmentation method. Okay, the popular architecture such as full convolutional network (FCN) and UNet, which is used widely in medical image segmentation. So this is an overview of a semantic image segmentation. Okay, where there is a person, bench, plant, grass, and also a cat. Okay, hiding at the maybe the feet of this girl. So each category is segmented into a different category and encode, okay, in a different way, in different, which have their own class for person, bench, plant, and cat. So the basic convolutional encoder decoder is a deep learning technique for compression. Okay, So encoder basically extract features by applying convolution and downsampling or pooling gradually reduces spatial dimensions while increasing features depth. And the decoder here basically reconstruct the segmented image by applying upsampling or deconvolution, gradually increase the spatial dimension, okay, producing pixel-wise predictions. Okay, so in this basic picture, you can segment the cars, the road, and also the scenario or the scenery into each segment. So the encoder compress the input image into a latent representation. Then the decoder maps the representation back to the original resolution for pixel-wise classification. So the popular model is SegNet, use symmetric encoder-decoder structure with max pooling indice for efficient upsampling. Okay, UNet is one combined encoder and decoder with skip connection for precise localization. Okay, so so now I'll be talking about the SAM. Okay, SAM is the segment anything model. Okay, basically it's developed by Meta AI, formerly known as Facebook AI Research, to advance image segmentation for diverse application. It's versatile segmentation, support the three segmentation that I mentioned just now: semantic, instance, and panoptic segmentation. It is trained on a SA segment anything 1 billion dataset. Okay, this is the name of the dataset, which consists of 11 million images, 1 billion masks, excellent in generalization of unseen data. Okay, so it is very comprehensive dataset for indoors, outdoors. Okay, and then it is promotable segmentation, which means is accept points, bounding box, or mask to guide segmentation. So the architecture is a hybrid of CNN, and the attention-based model combines convolution layers for features extraction, attention mechanism. The key component use image encoder, prompt encoder, and mask decoder. Okay, so the innovation in SAM, it use attention gate to focus on specific image region, high-speed performance, real-time segmentation, respond in millisecond. It's very fast. Okay, you can get the performance for tracking, especially SAM2. You can detect an object and also do the tracking, almost real time, and works on diverse object and scene without fine tuning. So this is the architecture of a basic SAM. Okay, you have the image encoder, and then image embedding, and then this is where the downsampling must happen. Added the mask, and then there are three prompt encoding. It can be point, box, or the text. And then the valid mask is scored based on the confident and scored. Okay, these are the example. If you want of an image of a Caesar, if it is partially detected, and then maybe the confidence score is less than the wholly detected Caesars. Okay. So SAM limitation struggle with video segmentation that requires additional model for temporal data, not optimized for real-time performance in video setting, and SAM2 expanded to handle both image and video segmentation. Okay, SAM1 basically only can handle image, but SAM2 can do both image and video segmentation. The key innovation is unified architecture for promotable visual segmentation in videos. Okay, you can prompt, okay, whether it is point, box, or the frame, and support temporal segmentation by predicting object across videos frames, and includes memory attention for tracking object across frame, more efficient handling for diverse prompts such as for point, box, and mask. So this is an example of SAM. Okay, you have the ball and you have the image encoder, mask decoder, prompt encoder. So when it click to the dog and the ball, okay, it is detected, and then there is a memory encoder. This is for basically for images, and then for video, there will be a memory bank, and the memory attention will do the tracking of the ball and also the dog. Okay, so this is one of the example, the video. Okay, I will explain in detail after this. Okay, we go to the next. So the segment anything 2 model, data engine and data set. This is the promotable visual segmentation, which consists of box, point, and mask. And also the segment anything model, which consists of prom encoder, memory attention, image encoder, memory bank, and mask decoder. And the data set is very SAV, segment anything video data set. It's very annotated video data. It's a large data available for research use. Okay, the image encoder here, okay, basically is hierarchical mask auto encoder that allows the multi-scale features during the decoding. Okay, this is the decoding part. Okay, to reduce the dimension and do the downsampling. Furthermore, the image encoder encodes the video frame streaming and encoding one frame at a time. So the memory attention here is the cross attention mechanism that condition current frame features based on past frame features. Prediction and prompt. This achieved through stacked transformer block, with the first block extracting the current frame. And then the prompt encoder here, okay, there are the process various prompt types similar to SAM, but there are two types, which is sparse and dense prompt. Sparse is the point and bounding box, okay. Use positional encoding and learn embedding. The dense one are managed by the convolutional layers, okay. Okay, this is the mask decoder, okay. Mask decoder is located here, which receive the image embedding and also the output token and prompt token as an input. The output is the mask value, object pointer, and also intersection of union scores, and also the occlusion scores. The memory encoder here encodes the current frame prediction and image embedding to be utilized in future frames. Okay, and then the memory bank store past prediction, but only for the target object in the video. It also maintains the history of prompts for the frame that were prompted. So let's talk about the data set. Okay, the segmented anything video data set is the largest segmentation data set for video. Includes millions of video frames covering diverse scenario, comprising of 54% indoors and 46 outdoor scenes. Each video is around 14 seconds in duration. The video span over 47 countries with highly varied environments. The frame include in the wild scene with everyday scenario. So basically, it covers all scenarios, okay, indoors and outdoors, okay. Okay, these are sample of the data set available for segmentation. Okay, you can Google and see the if you and also go to the GitHub repository. Okay, this is the address. If you have a video and you want to test the segmentation on SAM, you can use the running inference on video to check its capability in real world videos. Okay, so it's online. Okay, whether you install the GitHub or Meta Hub, go to Meta Hub, search Meta AI SAM 2 in Google, and then it will redirect you to the real demo of the segmentation, providing your own video using their own their inference available online. Okay, the practical example. Okay, SAM can be applied to various image segmentation tasks. for binary semantic and instant segmentation. Okay, practical application include medical image analysis, autonomous driving, and satellite imagery. Using SAM in this domain improves segmentation accuracy and efficiency. Okay, this is an example of apa, medical image analysis, the application, and also this is our own work by my previous PhD student, Dr. Susama, on the mammogram detection of lesion location or cancerous cell in mammogram. Okay, so to check whether it's malignant or benign. So we have used the segmentation technique, UNet, and also SAM in this in our research. Okay, and also this is the mass identification result. Okay, for several anchors, 8, 11, 14, 15 anchors, and 17. Okay, so this is not predicted because the mass was not identified by all the images, where the green box is the ground truth. Okay, so basically we have used the technique and applied in our research and give good results. And this is SAM2 application for tracking object to create video effect. You can see the segmentation of ball 1, ball 2, and ball 3 happen, and this is segmenting moving cell in video captured from microscope 8 in a scientific research. Okay, if you are a bird watcher or maybe a butterfly watcher, and you can do an application on segmenting on butterfly and do tracking, okay, in animals, moving animals, and birds, and so on. And this is a preview of SAM2 web-based demo, which allows segmenting and tracking object in video and applying the effects. Okay, you can see the seamless segmentation happens. Okay, okay. In future, AR glasses may employ SAM to recognize commonplace objects and provide helpful reminders and instruction. Okay, you can see while one person wearing the AR glasses, okay, the objects are detected and are labeled for the information and maybe the step in cooking. Okay, it is segmented correctly. Okay, this is one of the application of SAM2 application. And then in semantic segmentation for clothing stores, okay, the each clothes can be segmented and then it can be interchangeable. Okay, maybe a person have to, when enter the store, maybe take a picture first. It can do some segmentation and change only the particular shirt, or maybe for choosing which one is suitable, okay, in the clothing store. And then maybe object detection and classification for interior objects. Okay, where you have the kitchen features in the kitchen. Okay, it can customize which object should be located in the interior object. Okay, in the kitchen, for example. Okay, this is one of the example of SAM. Okay, as a conclusion, SAM is a powerful deep learning architecture for image segmentation that can handle a wide range of segmentation tasks efficiently and effectively. By understanding the theory and the PyTorch implementation of SAM, accurate and efficient image segmentation can be performed. Okay, that's all for my presentation. Thank you. Back to Mr. Chairman, Dr. Nan.
you very much, Dr. Zadi, for a very insightful presentation. We now have 5 minutes for any question or opinion. Raise your hand and the microphone will be passed to you. One question here, Dr. Sorry. Assalamualaikum, Dr. Zadi. How long does it take to is there any limitation or maximum object number and we detect the time?
Okay. How? I just want to rephrase the question. How long does it takes to train? And there is any limitation of maximum object number can be detected at a time. Okay. Currently, we use the inference provided by the if using the SAM, it's online. Okay. If it you can also build your own inference. It but it takes uh, uh, a high computer. I mean, the in terms of the computational time and also value, it's takes it takes quite a long time. Okay, because the data set is very large. So for researcher who want to test or want to try this detection technique, maybe I can share with you the hold on. I can share you. You can just go online and use the instances available. Okay, in GitHub, and then it can be used. Okay, but to make it if you want to make it from scratch, okay, it takes quite a good computer. I mean, in terms of the processor, and also it takes a lot of time. Okay, so for a starter, I think in terms of research, the data set is available, and then you can start. Maybe if does not give a good result, maybe possible to add the data set later. Okay.
So how big is the data set itself?
As I mentioned earlier, maybe I can share again the slide.
Can we train using the normal laptops, for example?
Yes, yes. The data set available online is quite big. Okay. Uh, and then maybe I can share you some of the video of the address. Hold on. Send to AI Maker. Okay, this is the website for introducing SAM2. Okay, the data set is available here. Okay, and then if you want to try Meta AI, okay, just click here, and then you need to log in first. Okay, obviously I cannot do, but it's possible for research. The demos is available online. Okay, you can try. This is segment anything too.
Understood.
Yeah. Okay.
Okay, Dr. Swairasari, answer your questions.
Thank you.
Any other question?
Any other question to the audience? Questions to Dr. Muzari?
To those maybe from UTM or from okay, we have one question. Any differences with using YOLO? Yes, different architecture, and different application and segmentation technique. Okay, it depends on YOLO. YOLO uses deep learning technique. Okay, but this application is for segmentation. Okay, you can use the demo online and use you have your own video or images, you can get the GitHub installed in your computer, and then do the segmentation. Okay, so basically it's a different architecture with YOLO. Okay,
Oh,
it's yeah,
sorry,
it's
another
not the same. Yeah.
the previous one. Is there any limitation or maximum object number can be detected at a time? Be that in one certain moment, how many objects to be detected? No number. 1,000.
Oh, okay. How many object can be detected?
It depends on the hardware itself.
Yeah, it depends on the hardware, and also the architecture and the way you train the system. But if you use the apa the one provided by Meta, and then almost every scenario is there. Okay, whether it is indoors or outdoors. Okay. Uh, okay, you can just load any demo, and then use your own data. For example, okay, this is okay. For example, I want to track here. I want to track this ball. Okay, I just focus in this ball, and then add the object, and then track the object. You can see it is tracking the our my video. Okay, for this ball. Again, if I want to track, I remove this one. I stop first, remove this one. I want to track maybe the shoes. The shoe. Oh, I need to go back maybe. Start over. Okay, I want to track the shoe. I just click to the object. These two shoes. Okay. Oh, remove one. Okay. I want to track these two shoes. Track the object. Okay. You can see it is trackable. Okay, you can just put your own video here and then do the tracking. Okay. It seamlessly do the segmentation and tracking. Okay, you can put your own video here. Okay, okay. I think that's answer the question.
Here's also another question. The last from Adika Rashid. Is it applicable for P2V, text to video?
Sorry, I cannot hear you. It's applicable to text to video.
Text to video. To video. Text to video.
No, no. It's it can do the images and video. Okay, if you want to, you have a lot of images and you want to do like medical images, you want to do the tracking, it is possible. And then for text, the application might be possible, but if it is used in images and videos, basically.
Okay, thank you very much, Dr. Nazani. Right. Adika Rashid's questions. Okay, in our session for today,
Okay, thank you.
5 minute break before our next presentation, which is by Associate Professor Dr. Muhammad Fazalul. Okay, we will start by Yes, Assalamualaikum warahmatullahi wabarakatuh. And indeed, a very good morning today, a very sunny day today in Batpahar. Next, we will have Associate Professor IR Dr. Muhammad Hafiz bin Fazalul Rahiman, representing MyCT, who will be discussing revolutionization image construction in tomography via machine learning. Without further delay, I'd like to invite the associate professors, Dr. Hafiz, to very warm welcome. The floor is yours, Doctor.
Assalamualaikum and
Good morning, everyone. Thank you for having me. And thank you to Chair and the Conference Secretariat for inviting me to deliver some sharing this morning. So I would like to share my screen now. Let me project my window. Okay, could you please let me know whether you can see my screen?
Here you can see your screen right now.
Okay, thank you very much. Let me have a second screen here. Not in full screen.
Pardon, Doctor?
Okay,
Okay,
now full screen. Full screen. Mm. The size of the Okay. I'm sorry. The screen is cannot be in a full screen mode, but then I think the image is quite sufficient for me to share. So leave it like that, lah. Okay. Basically, the title today that I would like to share is revolutionize image reconstruction in tomography via machine learning algorithm. And this project is part of my PhD students, Dr. Lee Chao Ching, where we work out on the machine learning approach to reconstruct an image for the purpose of tomography. This is basically your what you can see from a tomography systems. We have two kind of tomography system. Number one is the CT scan, or we can say computed tomography scanning, which is a medical devices that has been used to scan an internal organs for diseases and hospital usage. And number two is what we call process tomography. So the one that shown on the screen is the process tomography. I've shown here is the electrical impedance tomography. Is a method of using an impedance technique to gather the image around a column, and we can obtain the image within the circumference of the column depending on the materials. It can be a liquid and gas, it can be a solid and liquid. We also have another method of electrical capacitance tomography, which is based on capacitance sensor. So we make an array of capacitance sensor around the column, and we can obtain the image by using several hardwares like data acquisitions and laptop. We can gather the information and reconstruct the image, what is inside happening inside the column. And to look at a better picture, a main component of tomography system, we can split into three parts, which is number one is the sensing systems, and number two is the data acquisition systems, and number three is the image reconstruction systems. Image reconstruction algorithms. On the sensing system, we'll be looking at kind of sensor arrays and some circuitry for signal measurements. And for the data acquisition, we have the interfacing part, which collect the sensor data and have some pre-processing data pre-processing to feed into the computer for the reconstructing image purposes. We basically we have two kinds of tomography. We call it hard field and soft field. In the hard field, we have three types. Majority most on the X-ray tomography, optical and ultrasonics tomography. Whereas in the soft field, we have several kind, such as electrical impedance tomography, electrical resistance, electrical capacitance, microwave, as well as the one that I would like to share to take part of our case study in this research is the radio tomography imaging. The principle of tomography basically in the radio tomography imaging, before we jump into the image reconstruction section, is basically depending on a number of nodes here. You can see this is the green dotted line, and this green dotted line, to indicate the RF node, and the dotted line here is the line of sight or the RF link to be communicated between the transmitter and the receiver. And we can say the line of sight will pass through from the transmitter to the receiver or vice versa, and any object or obstacles between will be distracting the signals, and we can have some information extracted from the signals to then reconstruct the image. And as a general problems in this issue is, number one is the performance of the tomography system hugely depends on the number of sensor. We understand that the number of sensor could increase our data. The more sensor we have, more data we could gather, more precise image that we can use to represent the subject. On the other hand, number two, mostly in soft field tomography, in this case is radio tomography imaging, the number of sensors is limited because of the size of the sensor, or what we call here is the RF nodes, is quite a size, with the size of about 10 centimeter by 10 centimeter approximately. Can go down to 3 to 4 centimeter by 3 to 4 centimeter. And also it limits the size of monitoring area, because if you are using the RF, there should be some what we call Fresnel zone or near field and also far field region that we need to understand. We cannot have a small item. We also cannot have a too huge item, because this will tends to create what we call interference. So that must be some kind of prerequisite to abstain our tomography from having a noise data. Now, so to solve this problem, we propose a deep learning based image reconstruction or a reduced sensor model. So in this case, we would like to demonstrate that having used a machine learning based reconstruction algorithm, we can also rely on this algorithm, then we can reduce the number of sensor model. So a conventional method, the more sensor that you have will give you more data. So for this case, if you reduce the sensor data, you also reduce the sensor dependency, then our algorithm will suffer from poor reconstruction quality. But then here comes the good part of the machine learning. It will improve no matter you can work on a minimal number of sensor, but you still can yet maintain a very good quality of image. So you can see that in comparison with several other tomography, we have 16 nodes or 16 sensors, ERT and 16 sensors, and ECT can goes up to 7 sensors, but you also have some 12 sensors, and the microwave tomography also have 16. So all these red dotted is the conventional method or the existing that widely used in most of the research. But in our reconstruction algorithm, we would like to try only 8 units of sensor, but then we could also maintain the similar quality of image. This is the common reconstruction algorithm that being used currently in our tomography systems. We have linear back projections, which is quite popular method. We also have filter back projection algorithms. We have Newton one-step error reconstruction, or we call it NOZER, and Tikhonov regularization, TR. So basically, most of them is a discretized mathematical equation that we can feed into our computer systems, and it shows that most of the data must be heavily depending on the computer iterations and computation. So we need a huge GPU, or we need a huge processing power to compute the image. So let's move on to the comparison of the existing our deep learning image reconstruction algorithms. So there is another method that they use existingly, where they have this image, then they construct the image using existing image reconstruction, then they learn from the image, and then they reconstruct again using a deep learning. So the traditional image reconstruction algorithm have a significant impact, because if you want to have this good image, you need to have a lot of sensors. So by having a lot of sensors, say that 20, 30, 40 sensors, then you go and reconstruct the image, and you obtain the image, then you need to train in the network. So we don't want that to happen. So we are going to use data to image method, because image to image purely depending on the sensor data. But here, because we reduce the number of sensors to 8, so the data must be limited to 8 nodes, then we have our algorithms and we can reconstruct again. So let's look at our second proposal. Because of the data usually we solely depends on 8 data now, so the signal to noise ratio has been reduced. So we have to make sure that the signal to noise ratio is maintained by having only 8 data. So we have to clearly make sure that the data imported from the sensor is noise free. So in this case, we propose a data pre-processing method for the DNN, because when we collect the data from the sensor, if it has noise, then the training data will be hampered by the noisy signals. So this is our methodology. This is our methodology on how we reconstruct the method. So number one, we have to do the modeling of the RTI system. So here we can do the modeling using a console image for image sensitivity matrix, or we call it forward problem solving. And in the tomographic reconstruction, we have basically two, which is forward and inverse problems. So the forward is to estimate the radiance of the radiation from the sensor using a finite element analysis. And the inverse problem is a mathematical solution using the data obtained from the sensor to predict or to back project or to reconstruct again what has been transmitted to them. And the modeling next goes to input data pre-processing for DNN. So we combine here a pre-processing data to have a clear image as compared without the pre-processing. It's very hard for us to train the data. And finally, the image quality assessment. And you can see here, this is the mathematical model for the sensor. We have a circumference of about 1 meter. We have the sensor node. In this case, we use 8 sensor nodes. Both of them are, we can say, transceiver capable of transmitting and receiving. And we have also the specification table here to show that our operating frequency is only 2.4 gigahertz with a power of about 1 milliwatt. And we also obtain some of the parameter of the property of air and water, in this case, to just observe the differences and to test or to gauge our sensor capability. And when we put our test phantom here, in this case, the test phantom will be the what we call the subject or the obstacles for the sensor to read. So in this case, to obtain the 2.4 gigahertz, we use a simple, you can say, a non-MCU or ESP8266. Also, we can use a ZigBee, any 2.4 gigahertz ZigBee transmitter. So in this case, in our research, we use a ZigBee or XB, is in a commercial name. And after we obtain the parameter, we reconstruct or solve the fault problems using a console to look at how the radiation goes if you have one node transmitting the 2.4 gigahertz. So these are the radiations coming out from each sensor nodes to see that the radiation is moving from one side to the other side or to the other end of the sensor. And basically, the way how we communicate is when we have the sensor, when we have the image will be formed into one back projection image or reconstruction conventional method to get this image. But now we want to have a deep learning to be involved, so we are focusing on supervised, feed forward, fully connected, and back propagation network. Okay, and the simulation data set preparation is here. So on the right hand side is the algorithm or the pseudocode that we use to train the data, and basically we use a training set of about 16,800 samples, and we use another validation 3,600 samples and a test set of 3,600, which brings us to 24,000 samples. It's quite a number of data that we use to train. And these are the test profiles we use to simulate, and also we use to test. We have two kinds of test profile. One is the uniform test profiles. Number two is the non-uniform test profile. So in the uniform test profiles, we have most of the subjects having similar subjects. Like this is a small shape of 0.31 meter. We have both of them 2. We have both of all of them 3 and 4 in phantom A, B, C, and D. And when we have a smaller, we call it medium. We also have a small version. So these, most of them having the similar phantom or similar diameter or shapes. And for the non-uniform test profiles, you also have phantom A, B, and C, and D. Whereas in each phantom, A, B, C, and D, they have different kind of sizing. One is 0.2, 0.3, and 0.2. So another one is 0.4. So the detail is here, 0.31 and 0.2 and 0.18. So we have several of them with different sizes, just to see that when we reconstruct the image using deep learning, they can the deep learning can recognize the image. So to train the process of training the DNN model, this is the chart, or we can say that the block diagram of the processes, and the training will be based on using a Google Colab database. And the input pre-processing method, we include what we call a threshold because the data from the 2.4 gigahertz can be noisy. So when we have a threshold level, we can set to cut off the noise before it goes into our processing data. So the data process will clear or free from noisy, from ambient, or from any disturbance externally. And after reconstruction, we would like to gauge the quality of the image. So we use two parameters, which is MSIM, AMSSIM, or mean structural similarity index, and also we use area error, AE, using both equation. These two are the generic, or we can say a popular model that has been used for quite some times in the research. So these are the setting that we have. We have a 1 meter diameter subject. We have a water medium as our test subject, and this is the XB RF. And basically, the configuration of standard ZigBee is quite popular. So we will use WSN architecture with star topology. And let's look at the results here. we have several results that to be shared. We have two parts. Part one is DNN only. We can see the results later on. And part two is DNN with the input pre-processing. And this is the image reconstructed from a simulation data. The uniform test profile and non-uniform test profile. 2 phantom and 4 phantom has been used as for our slide here because we have limited time and also space. And the right hand side here is DNN method, and the other 4 column here is LBP, linear back projection, filter back projection, nozzle, anti-con-off, and this is the simulated image. The test profile here is the subject that we use to simulate, and the simulation results is showing here using a COMSO simulation model. And the reconstructed images using conventional method shows quite poor image of from the simulation model. And when you look at the DNN simulated, we get a proper results. So this is a nicely indication to show that our model works. Okay, so the result shows that the result from the DNN supersedes most of the conventional method, okay, which is in blue in color. If we conduct the experiment part just using DNN without processing, but the results in simulation does not include pre-processing because there is no noise. To prove that there is no noise data from the simulations, so a simple DNN could solve the problem. But then if you conduct using experiment, a simple DNN could not reconstruct the image. This is poorly reconstructed. This is the DNN using experimental data. If you compare with the simulated data, the works of DNN is very interesting and looks sharp. But then if we compare with the simulation, it does not look nice or does not look to replicate the phantom profile. So this is another phantom where we have more of the subjects inside the portion, and the DNN fails to recognize. So for this reason, that gives us a motivation to include a pre-processing, and having input pre-processing method, we could increase the MSIM value up to 0.7. So the highest is 0. The highest is 1. The lowest is 0. Previously was 0.2, but now we increase up to 0.7. So you can see here, most of the noise has been cancelled because of our input pre-data processing. And you can look at here, how do you obtain the threshold for pre-processing is by having some ranging of thresholding from 0.1 until 1.0, and we capture for each phantom what is the highest threshold that leads to the lowest error, and we capture this number and then we feed into our model. So this is the comparison with the reconstructed images from experimental data for uniform and non-uniform. We have LBP having the worst, FBP, and we also have nozzle, Tikhonov. But then when we have DNN on the left-hand side for the uniform test profile, we also have uniform test profile for 4 phantoms. We also have a non-uniform test profile, and also another one for 4 phantoms of non-uniform test profile. It clearly shows that the DNN are able to distinguish the subject efficiently. And of course, looking at the pictures and the graph also tells you the same. The DNN supersedes most of the algorithms. So as a conclusion for this research is the deep learning image reconstruction algorithm for reduced sensor model has demonstrated successfully by using only 8 sensors instead of more than 8, like 16 or 32. And input data processing, pre-processing method for deep learning method able to improve the DNN reconstruction images from the image itself is clearly shown that the DNN supersedes most of the conventional method and compared with the traditional LBP, FBP, nozzle, and Tikhonov. And it has been validated using MSIM and AE or area error matrix or parameter. And this is the end of the slide. Thank you very much. If you have any question you want to
Okay, thank you very much,
you
Dr.
want to
Hafiz.
ask, you can ask. Thank you very much.
Thank you very much, Dr. Hafiz, for sharing your expertise. We will now like to open the floor for question. If anyone would like to ask any question regarding
I think the mic is not on.
Okay, thank you very much, Dr. Hafiz, for sharing your expertise. Now we'd like to open the floor for any question. This is your opportunity to ask anything to Dr. Hafiz. I believe that there's one question there. From Yasmin Minta Abdul Wahab, what is the meaning of uniform versus uniform testing profile?
Uniform and uniform. Uniform means the shape of the model. Yeah, I just show my screen again. Uniform means the you can see the screen. Uniform means the slide shows that the pictures of each subject is similar to the other subjects. For non-uniform, we have two different kind of sizing inside of the column. The reason why we have different sizes is because we afraid that we have a false data while training, because this deep learning, it can be reconstructing idea that maybe it duplicates. So we want to test the bottom line whether or not the deep learning functions. So we split into two different profiles. The uniform, we have all the same sizes of subjects inside one column, and the non-uniform have several, like 2 to 3 subjects with different sizes in the column, just to give us a better picture whether or not the deep learning functions. I hope I answered the questions.
Okay, thank you very much, Dr. Hafiz. Next, question from some request from Nur Rashika. Doctor, can you share your slide afterward? Maybe in PDF after your.
Boleh, tak ada masalah.
Share.
Boleh.
Next is from Associate Professor Siti Zarina binti Muhammad Muji. Is the deep learning algorithm will be downloaded inside the controller, meaning that the model itself, after you train everything, is it required to be downloaded to go into the controller itself?
No, we use Google Cloud in this case. So our controller will be the Google Cloud. So we because when having deep learning, we have lots of data. Although we have like Jetson and most of the GPU available, but it's quite costly. So we depending on the Google Cloud now, a simple subscription. You can upload our data, and our data will be processed in the cloud and give the results in a very short while.
Okay, thank you very much, Doctor, for the very pleasant sharing and very educated, of course, answering all of the questions. Again, we'd like to thank you for your time. In continuing our session, we'd like to ask to continue with the third invited speakers, which is Engineer Dr. Fawad Salam Khan from Air University. Meanwhile, we would like to take a 5-minute breaks, and we will continue again around 12:10. Okay, thank you everyone. Assalamualaikum and hi again to everyone. Now we are moving to our third speaker, Engineer Dr. Fawad Salam Khan from Air University. Dr. Fawad will be present on reinforcement learning for predictive maintenance of biomedical equipment. Without further delay, I'd like to invite Dr. Fawad Salam to present his speech. Please give a big round of applause for Dr. Fawad. Okay, Dr. Fawad, the floor is yours.
Okay, good morning.
Can hear you? Very clear?
Can I share my slides?
Yes, yes. Yes, please.
Okay. 1 minute.
We can see your screen right now.
Have you seen my screen?
Yes, we can see your screen right now.
Okay. So good morning to everybody. I am Dr. Fawaz Salam Khan, Assistant Professor AI and Data Science in Department of Creative Technologies here at University. So today my topic is based on the topic reinforcement learning for predictive maintenance of biomedical equipment. Some of the there is some internet issue. My internet is slow. 1 minute. So the abstract of the presentation is on the predictive maintenance. Basically, first we are going to understand why this topic is important and the reinforcement learning in predictive maintenance, which is like to offers a promising avenue to improve the reliability of biomedical equipment, such as normally in this era, MRI machines and ventilators, which are quite much expensive and have some issues related to their downtimes. So we are going to design some kind of a real-time analysis and optimization of maintaining schedules. So this presentation focus on leveraging RL to minimize downtime and reduce cost by integrating different IoT sensors for real-time monitoring. For example, if you are talking about the application of RL in biomedical equipment maintenance, which can be a challenge, such as reward and scalability of such equipment, which can be an advance in multi-agent and deep reinforcement learning, have and potential address to this area. So once my, is my presentation is working properly?
Yes, yes. Right now it's in abstract speech.
Okay. So first we are going to introduce the predictive maintenance, how the predictive maintenance is important for the biomedical equipment, especially when we are talking about the reinforcement learning, which is again a type of a machine learning algorithm. So predictive maintenance involves using different analysis to predict equipment failures before that occurs. So this helps in minimizing downtime, reducing maintenance costs. So normally, if you are talking about the biomedical equipment like MRI machines and ventilators, which can have a maintaining equipment reliability and crucial for patient safety and operational efficiency. So once we are going to have some kind of predictive maintenance, so we are going to or have different concepts related to reinforcement learning, where agent can perform different kind of relationship between the environment and get input in observations to minimize the downtime as a reward. So now we are going to understand what is a reinforcement learning. So reinforcement learning is again is a type of a machine learning which has five different components like agent and environment, observation, reward, and then have some kind of a policy where an agent learns to make decision by taking action in an environment to maximize the cumulative reward. So there can be an immediate reward. For example, the agent learns different uh, from the data analysis. It has some kind of an input, then get reward to perform different actions. So in particularly effects in different scenarios, it can have an optimal strategy which is not known initially. So it can use different hit and trial methods to learn different scenarios to minimize the downtime of the ventilator or any kind of an MRI machine. So, why it is important for the biomedical equipment? Again, this is a very emerging field. If you are talking about the biomedical engineering and soft robotics, where we can design different actuators and have different sensors. So, normally these equipment plays a vital role in diagnosis, treatment, and monitoring of patients, which can ensure these devices function correctly and reliable, is essential for healthcare providers to deliver high quality patient care. So whenever we are having different issues related to a machine, where no, where we can have different downtime scenarios, so this can make a disaster for patient care. So once this algorithm can design, it can not only downsize the time of the system, but also make a proper decision by itself. For example, if there is no doctor available at the in the hospital, and for example, and this machine is required, it can automatically make decision by itself as the algorithm learns to minimize the downtime. So there can be multiple challenges in predictive maintenance, especially when we are talking about by implementing predictive maintenance in biomedical equipment, which have several challenges like data scarcity, sensor reliability, and complexity of medical devices. As we know that biomedical equipment consists of different sensors and actuators, and it has sometimes have different malfunction values, which can make sometimes give different or wrong decisions at the time of implementation. So whenever there can be a downtime, this can address different challenges which can affect the maintenance strategy. So the maintenance strategies, the data can have different values related to the input, and then have some reward values. For example, if we get some wrong values, and the model learns the wrong values, and it can have some a positive value, then it can easily detect this. Whenever it gets a new value, it will check out whether the value is right or wrong, and then it will make the decision by itself. So the role of data in the maintenance, you can say data is backbone of predictive maintenance. So not only in the deep learning, deep reinforcement learning also required data which can be used for the predictive maintenance related issues. In normally the sensors and the actuators have these values, and we can have a data set from these sensors. So whenever we are going to collect or analyze the data from equipment sensors, that allows for the identification pattern and anomalies leading to the time interventions before failure occurs. So why this is related to reinforcement learning, as I told earlier, that reinforcement learning and hit and trial method, which have a predictive maintenance to enhance the decision making process whenever it get the best reward, or you can say a cumulative reward, a positive reward. It will make different decisions. Like for example, we have different algorithms related to, like we have Markov decision process, we have Bellman equations methods, we have Q learning, and we have critic actor critic methods, where we have the different exploration and exploitation techniques, where the RL algorithms can learn from historical maintenance data, which can improve their ability to predict equipment failures and optimize maintenance schedule. So whenever reinforcement learning is applied on such algorithm, there can be various techniques, which is a model-based or a model-free environment. So we can have one case study, for example, a case study of on an application of reinforcement learning in predictive maintenance of MRI machines, demonstrated significant improvement in maintenance schedules and reduced time. So uh, we are going to have a different sensors data from different MRI or ventilators machine, and then for example, we are going to apply some kind of a Q learning method, so where we can apply a different sensors, we can get different sensors values, and then apply this algorithm. Once this algorithm is applied, the results can highlight the potential of RL in healthcare settings. So there can be multiple benefits of using RL. For example, the use of reinforcement learning for predictive maintenance offers numerous benefits, include enhanced accuracy, failure predictions, reduce operational cost, and improves patient safety. So most importantly, whenever we are going to design such kind of algorithms for biomedical equipment, not only for the biomedical equipment, anything related to which can have reward based systems. So the decisions by itself, no, as traditional AI contains predictive or classification or prediction issues, which can have, like you can say, if you are talking about learning, there can be multiple models for that. But here, reinforcement learning not only get a benefit by having a reward based function environment, and have their own decision systems. So successful implementation of RL and predictive maintenance requires structured approach, which can have, like in step number one, like if we say for the pre-processing type of thing, like data collection, model training, and continuous monitoring. Collaboration between data scientists and biomedical engineers is crucial, because this system can have a proper, you can say, a consortium between a biomedical engineer and data scientists for the design of such equipment. So future trends in the predictive maintenance can have the, like biomedical equipment promising with advancement of AI, machine learning, and IoT technologies. So here multiple sensors can be used by having different values, not only for the predictions but also have the classification related issues. So this development will let the more sophisticated predictive models and improve healthcare outcomes. So there can be also some limitations. While reinforcement learning present opportunities for enhancing predictive maintenance, limitations such as the need of large data set and potential bias in learning. So normally we have a data set from multiple patients from the MRI machine or from the ventilator, which can help us to train the reinforcement learning algorithm, which can have a careful consideration for these factors, which is essential for implementation on the sensor side. So, in conclusion, enhancing predictive maintenance of biomedical.
Kita orang nampak dalam tu nampak ni. Kita present lagi. Kita present.
Oh, dia present. Suara tak ada, suara.
Okay, thank you very much. This is my presentation. Any questions?
Thank you, Dr.
Do you have any questions?
Thank you, Dr. Fawad, for the comprehensive presentation. Now have a 5-minute question and answer session. Free to raise your hand. Any question? Question here. teaching aid, how to do RL, reinforced learning.
Can you write the question because the voice is not clear?
Sorry, there's a message there in message box. How to do RL? How to do reinforced learning?
Sorry?
How to do RL, reinforced learning, from
So reinforcement learning is basically based on the reward based learning. So there is an agent which is a sensor value which will get the sensor value from the environment. So these observations will get and have some reward, then produce some actions. For example, making a downtime to minimize the downtime, we can have multiple sensor data, and whenever we get this data, we will produce a reduce reward system for that. So whenever it will give the it will receive a positive reward, it will make some decisions to do or do not. It will make some decisions on that.
The next question, Doctor. Can we use reinforced learning in other application for predictive?
Hello. Have you got my point?
We've got another question, Doctor, from Muhammad Sazlan bin Abdul Qadar. Can we use reinforced learning in other application for predictive? Can we use RL, reinforced learning, in other application for predictive?
Can you write the question? I will write because the voice is not clear exactly. I think I have some internet issues here.
Okay, I think you already answered the questions. Another one, from Muhammad Sazlan. Okay, I will copy the questions again. Okay, this is questions. Can we use RL in other application for predictive? Okay, thank you very much, Dr. Fawad. Question from other fellow audience? That's it for again, I'd like to give a presentation now.
Can you all see this slide?
Yes, Raf, you can see it.
Okay. Just to confirm, it says activities tracking for assisted monitoring of child occupational therapy. Is that right?
Yes, indeed.
Hello? Yes? No, we're doing this online, so I have to ensure that
Yes, Doctor.
everything is...
We can see the activity tracking for assisted monitoring for child occupational therapy.
Okay. Okay. Sorry for that. It's just doing this online. You have to ensure that the audience is up to speed and keeping up with the connections and everything. So, bonjour, comment ça va? I'm actually in France now, so it's actually good morning from here. So my name is Zaid Omar. I am the head of Digital Signal and Image Processing Research Group from University Technology Malaysia, UTM. And I will be presenting a research that I'm currently doing. This is a research in progress, of course, but I just want to share some findings and some outputs that we have made. The topic is a little different from what I gave in the schedule. So the topic, sort of a more specific and focused topic, is actually activities tracking for assisted monitoring of child occupational therapy. So I'll be introducing the concept of the problem statements and a little bit on the literature review and methodology of how we did our solutions and the algorithms that we used. Discuss on the results and discussion, and wrap up with a conclusion. Now, for introduction, some of you or many of you may know about occupational therapy, but just for those who are not familiar, occupational therapy is a therapy session that's directed to children with disabilities. So this would include children with autism and ADHD and global developmental delays and such. So occupational therapy is a session such as you can see in the picture here. It consists of maybe a sensory room that has many different activities where children is free around to play with the activities, and there are therapists in the room who will observe and guide the children as they are playing. Now, the conventional or what happens in occupational therapy is that therapists will assess the children's activities and their progress and so on. But this will this will cause that the therapist will maybe have a bit of difficulty to monitor multiple children at the same time and to assess their progress and their performance and the activities at the same time. So what we want to do as computer engineers is we want to automate the process of analyzing child behavior. So we want to help the therapist to assess the children's concentration, their responsiveness, and their interaction in order to help them. Now, when we're talking about this, so of course we can use person detection and person tracking and so on, and many works have been done on these person detection algorithms and works. But when we're talking specifically on the specific problem that we want to solve here, it involves child tracking and observing what exactly the interactions are. So the problem is not as general, it is quite problem specific, it's quite focused. And with that, we have initiated some previous works that I did with my previous students. So first of all, we have works by Zewil and then by Co. So we did have some preliminary works, but there have been some, I guess, gaps or limitations of their works, which we want to improve in this particular paper. So moving on to literature review. Occupational therapy, what it is, like I've mentioned, it's an intervention session, like a therapy session that focuses on motor skills, sensory skills, and cognitive skills. And what happens is that children who are exposed to occupational therapy, they tend to, yes?
Is that your slide? Is it moving or still static in the first page?
It's supposed to be moving.
Currently, it's still stuck in the first page, and
really?
it's currently in called editing view mode.
Hold on. Let me present again. Sorry about that. So should I share the entire screen, right?
Yes, or you can, another solution is you can use, instead of using a full screen presentation mode, you can use
Mhm.
reading mode. And using that mode, you can minimize, you can make the window smaller.
Okay.
Although you
So like
sharing,
this.
we are seeing your calendar here.
No?
Is your calendar, if I'm not mistaken.
Is this right?
Can you share? Can you share the? You can. Can you go to the screen where you have your PowerPoint?
Okay. Yeah, got it.
Right now, you're showing your calendar.
Hold on, let me tutup my calendar. Okay, is this right?
This one. Go to the
Okay.
bottom of the page.
Okay.
Try to click the button number, the third button.
Reading view.
Reading view. Yes.
Okay. Is this correct?
Okay. You already press the reading view mode, right? Then
Yes.
reshare your screen to the PowerPoint. Send
Okay,
something.
I'll stop.
Stop and reshare. Share the windows of the reading view.
Window or entire screen? Entire screen.
Just windows.
Okay,
The
hold on.
windows.
All right. Okay, can you see this?
Yes. Yes.
If I change, can?
Yes. Hold on. Okay. Try to move to the next slide. You might have delay there.
Next slide, this one? Can?
Somehow it's not moving in our slide. What about others? Yes, it's changed. It's,
So now it should open background.
now it's changing, but a bit delay dah. Jauh sangat Perancis.
I don't know.
I
funny,
think I think it might work. It might work. I think you can continue your presentation.
So now which slide is it now?
Part 1, introduction.
Okay, yeah. So belum nampak lagi agak gambar ni. So this is a picture of a occupational therapy room. So it is here that children are, they are free to play around with the various activities. And each activity is meant to stimulate the sensory and the cognitive and the physical skills. And the therapist will assess and observe and guide the children. So like I say, the issue is that the therapist may have trouble to observe and monitor multiple children at the same time and assess each of the individual activities. So we want to use AI, we want to use video analytics to help track the children and help the therapists in that sense. So if I move so now can you see a change in slide?
Not yet. Maybe another 5 seconds.
I think if I convert to PDF, maybe it will be better.
Perhaps.
Yeah, let me file save as PDF. Sorry about this. Kita pun tak biasa. Lamanya. Did not realize that there's the trouble with that. Oh, dia punya font lari. Tak apalah, kita try. Can you see this?
Yes, we can see the slide.
I think PDF better, tapi font lari lah pula. Tak apalah. Okay, anyway. So occupational therapy lah. So occupational therapy is a therapy that we want to, it's aimed at helping the children because research and science has proved that occupational therapy has been effective in addressing children's punya progress lah, especially for autism and ADHD and JDD student children. So this is just on machine learning, and we are focusing on YOLO. So YOLO is a very popular method for person detection. So we are using YOLO V8. And moving forward, more than just YOLO, because we are detecting persons and we want to detect the movements and the activities of children, we need to be able to detect the pose, the pergerakan, and the body parts of the children. So we had a look at different techniques, and we decided on a technique called alpha pose, which is YOLO based as well. So alpha pose, I will talk later. This is the technique that we have chosen for pose estimation. So moving on to the methodology. So the scope of task is to assist therapists by providing automated detection and tracking of the following activities. So this is where the therapists, when we sat down with them, they said that okay, this is the problem that we want you to help solve. So first of all, which play zones in the occupational therapy room does the child like to play at? So this is done by dividing the room imagine in the footage into regions based on the play zones. So the yellow lines there is the regions, and I will talk a bit about that later. Secondly is how much does the child interact with other children in the room? So the eye contact.
Prof, sorry again. I believe that right now we are seeing a part 1 introduction still.
Oh, yeah.
Perhaps you can share your PDF or your PowerPoint to us. We can.
Yeah. Macam mana tu?
Zarina, we can help.
Kenapa Kenapa jadi gini? I'll send to Dr. Zarina. Dapat ke saya sudah hantar dekat WhatsApp?
Okay, dapat. Kami tengah proses.
Window entire screen Chrome tab. Kalau kita Allah. Hilal. Hmm. Hmm.
Okay, Prof, at what page?
Sorry.
At what page should we continue?
Mana ya? Sekejap ni kita. Okay. Dah kat mana tadi? Saya pun dah lupa. Bawah lah. Go to methodology lah. Go to straight to methodology. Yeah. Okay. So this one. So this is the specific task that we want, that the therapists want us to help with. So first of all, they want to estimate which of the play zones, which of the activities that the children like to play at. And secondly, how much do the children interact with each other? So we define these activities in terms of image processing or in terms of computer vision. So the play zones are divided into regions or hexagons. You see the yellow lines there. And the child interaction, we define that as the eye contact. So how do we automate, or how do we estimate eye contact in terms of computer vision, in terms of image processing? So that's forms the rest of our presentation. So next. Next slide, please. Okay. So the data collection was done in collaboration with an occupational therapy center, Mindcare, Sendirian Berhad. And we collected some footage of children playing in the occupational therapy room, of course with the authorization and permission of parents and so on. And then we did some annotation, pre-processing. Next. Okay, augmentation. Next. Okay, so for person detection, I think most are familiar with YOLO. So we use YOLO V8. At that time that was the most recent, but now we have YOLO V10. But so we use YOLO V8 for person detection, which I think is the most state-of-the-art, I guess, the gold standard for person detection. And then we did training and epoch and validation loss and so on. Next. Okay, performance evaluation in terms of precision and recall. Next. Moving frame by frame, so we want to track the movement of the child, so we use bike track. So we use YOLO in conjunction with bike track to track the frame by frames of the movements. Next. So this is alpha pose. So from the person detection of the bounding box, we broke it down into the body parts, the individual body parts. So alpha pose is able to detect up to 17 body parts, including the head, the eyes, the ears, the nose, the mouth, the shoulders, hands, feet, and so on. So it's a very powerful tool for detection of body parts. And this is proven very important later when we want to do the gaze estimation of when the child, they are looking and interacting with each other. Next. So head pose, next. Too detailed. All right, so gaze, I think next slide. One more down. Okay, so this is how we do the gaze estimation. So we want to ensure which where is the eyesight of the child. So this is done by getting the midpoints of the eyes and the ears and the nose and the head, and we do basically a perpendicular line coming up from those midpoints, and we are able to basically estimate a child's gaze, the eyesight of the child. Next. All right. So in terms of the region of the play zones that we talked about, so we calculated in terms of the centroid of the regions. So centroid of the yellow boxes, and then we overlap them with the centroid of the child. So if the child's centroid is within the centroid of the boxes, then we will consider that the child is interacting within that play zone. So that's basically our definitions for the two tasks that we had. Next. All right. And finally, we combine all of that in a GUI, so created a graphical user interface that is able to create a dashboard. So what we want to do is create a dashboard that can perform an analysis or a summary of the whole month's activity. So this will provide a very easy tool for therapists that they can, print out the report to the parents at the end of the month. Okay, your child has been using, has been interacting this much over 1 or days, 2 days, and so on. So that's the GUI that we did. Next. And or performance valuation in terms of the FPS. Okay, next. All right, so these are our results. Okay, I have a video actually, but maybe I can share it next time. But basically, we were able to detect the child. We were able to create the zones, the play zones, the blue boxes there, and we were able to create the gaze estimation of the child. And we define as interaction between children taking place when the gaze, the lines coming up from the child's face, it meets with the line coming up for another child's face. That's when we know that the eye contact has been made and interaction has been made between the children. So that's what we did. And we can count and estimate how many seconds of interactions are happening between them. Next. All right. So this is frame annotation. Next. That's just the data collection. So we did annotation for our training, augmentations, brightness, hue, saturation. Next. All right. This is the YOLO person detection. Next. These are just numbers, and we were able to get a quite high, which means that our YOLO, the YOLO technique that we used was very accurate, very effective. Precision of 97%, recall 96%, and so on. Next. All right. Okay. So next. All right. This detection tracking. So these are the numbers that came out. Next. Okay. So tracking. So we are able to do a bit of tracking there. Some examples there. Next. All right. So this is the alpha pose and gaze detection. So the alpha pose, we were able to detect the children's body parts. Next. So that's the gaze calculation. So you see that there are lines or lasers coming up from the children's eyes. So that's actually the gaze estimation lah. So that's how we calculated the movements. There's a question there by Dr. Nozali. I can address that later. I have those in the slides. Next. Okay. So when you talk about gaze estimation and interaction, so of course, based on our kind of low resolution 2D camera, so there are inaccuracies. So first we have inaccurate key points because maybe it's low lighting and low resolution. Secondly, we have children that are coming in and out of the frames, that are out of the footage. So when they come back in, they are treated as a different entity, different ID. So maybe we can have a more bigger footage, bigger angle. And thirdly is the occlusion. So I think that's what you meant. Limitation from 2D. So what we suggest for future work is we want to convert this into a 3D or a stereoscopic camera that can take depth estimation. So when we do the gaze estimation, we can really, estimate when the child is looking one behind the other. Next. Okay, so this is the GUI that we did, very basic GUI, but it's got the bar charts. It's able to analyze. So let's take, for example, the blue and the orange blocks there. So you can see that child number 4 and child number 6, they do not interact very much. So they don't like each other or they're not interacting with each other. Child number 2 and number 6 interact a lot. So you can, this kind of interaction, you can tell the therapist and you can tell the parents. And same goes for child-adult interaction. So you have the therapist there. We can discriminate between child and adults as well. So you can see that maybe child number 6 is someone who's very open, very welcoming and likes to interact with adults. The purple bar there. So number 3, for example, child number 4 stays at polygon 1 for more than 50 frames. So you can see that child number 4 likes to play at play zone number 1 because he stays there for a long time. So that's the kind of analysis that we can do. Of course, this is very basic, and we hope to have a more insightful and sophisticated analysis. Next. Okay, so you can produce a report at the end. So you can say that, let's say, play zone 2 and play zone 4 have the least child participation. So maybe those are the most play zone that least popular, that children don't like to play. So maybe the therapist, they can do something about that. Child 2 is the most active and the most responsive. So those are the kind of analysis that we can do. Next. Okay, so recap and conclusion. Next. Okay, so just wrapping up my presentation. So our system is able to perform child tracking with a very high mean average precision and recall. The gaze accuracy is 92%, which reflects the reliability on our method based on alpha pose, but including the inaccuracies as well, which we hope to address in future works. So overall, this work has contributed the application of YOLO V8 and alpha pose towards fast and accurate person tracking, specifically for child occupational therapy assessment. So we aim to help therapists to conduct more comprehensive assessment using video analytics. So for future works, like I said, we want to maybe expand this to 3D or stereoscopic cameras like Kinect and Intel Real Science and so on. So last slide. So finally, thank you all for listening. So actually, I dedicate this presentation to my son, Harith. So he is the one with autism. So he has been undergoing occupational therapy since small. So as a parent, it's something that I like to. We want to be able to help and assist occupational therapy to help children like Harith and others like him. To have a better chance at life, inshallah. So thank you all for listening. Assalamu alaikum.
Okay, inshallah, Dr. Zaid. Thank you for his very insightful presentation, Dr. Zaid. There's 2 questions here. I'd like to recall the question by Dr. Nozali. What happened when the eye gaze is not in line with the interaction of special needs children? As you may know that ASD children have a tendency of problem regarding focusing and eye movement. Everything is very difficult to have interaction between them. How do you get to this problem?
Yeah, so that's a good point. So we are assuming, so we make the assumption that the head post is the eye post, but yes, there may be instances of head post is looking this way, but eye is actually going this way. So I guess that requires more data, more, I guess, higher resolution data to get the eye contact as well. But I guess this work is a good preliminary or proof of concept that we can use video analytics to help things like therapy.
Okay, thank you for the answer. And then from Dr. Tay Kim Gate, may I know the class in the confusion matrix? Where is the source of the data set? Perhaps you mentioned before in your slide. Maybe any more clear explanation on this part?
Right. So the data set, like I mentioned, has been sourced from a real occupational therapy footage that has been obtained in collaboration with Mindcare Sendirian Berhad, which is an occupational therapy center in Skudai in Johor. So we went down with them and we, get the agreements to record the footage for one session, around 1 hour long session. So those sessions, it provides a lot of movements, a lot of data for our training. So, for training, we just need frames. So we have lots and lots of seconds of footage to train our data. And we were able to get quite accurate results. But I do understand that maybe to get a more varied data, to make it more generalized, to make our system be able to be scalable to other situations as well, and we need more different kinds of footage data. We are working with UPSI, University Pendidikan Sultan Idris, the researchers there, to get more data as well, and also some other therapy centers around Johor. So it is a work in progress, but welcome all feedback and support. Thank you.
Okay, thank you very much. We do hope that by this kind of work, we will also support and motivate other parents with the same shoes to go forward to explore what alternative they can help SD kids to have a better future. Okay, thank you very much, Dr. Zaid. We will have a 5-minute break and continue with the next speaker after this. Okay, thank you very much, Dr. Zaid.
Terima kasih. Assalamualaikum.
Salam.
Au revoir. Salut.
Okay, welcome back to everyone. Now we have our first student speaker for today, Mr. Tias Rahman Amirullah from UTHM will present image reconstruction in FPGA. Okay, Mr. Rahman, the floor is yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Thank you, Doctor.
Assalamualaikum.
First of all, my name is Rahman bin Amirullah and I'm a student of UTHM. Okay, let me share my slide. So, can you see my slide?
Yes, we can see your slide.
Anyone can respond to me? Can you see my slide now?
Yes, we can see your slide.
Okay. First of all, today I would like to share my research work. So this is part of my research work. So the title is image reconstruction using the FPGA. Okay. The content of my sharing today is start with the introduction. And the second one, why FPGA for image reconstruction? And next is key components Okay, workflow overview, implementation, benefit of FPGA in image reconstruction, and the future direction of this work. Okay, for the introduction, what is FPGA? I think most of us already know what is FPGA is. It's the short word for field programmable gates array, which is a versatile type of integrated circuit that is designed to be reprogrammable. Means it can be reprogrammable. Okay, programmable hardware device for custom digital logic design. Okay, and what is image reconstruction? It is a process of reconstructing an image from partial on noisy data or from a data. Okay, the next one is why FPGA for image reconstruction. The first one is because of its parallel processing. Okay, the FPGA can handle multiple image data points simultaneously. In my case, it will be very good point for me in my work. Okay, and then custom hardware acceleration, we can compare to the operating system or maybe like a computer. So this hardware acceleration, because we can do the acceleration because of the parallel processing. Okay, and the last one is the FPGA can do the real-time processing, which is efficient handling of higher resolution image and complex operation. Okay, the key component in my work is the input data, which is input data from the sensor, which is raw data or a partial image data. And the reconstruction algorithm I use is the technique is the FBP, filter back projection. Okay, and then there is processing core. I means also we can call it pre-processing. And after the project, after the reconstruction process has been done by the FBP. Okay, I do image segmentation, which is the simple one with using the thresholding, only the thresholding to remove the background. And then the output data, the reconstructed image, ready for display or further analysis. Okay, this is the workflow overview of my work. Data acquisition. Data acquisition in this block, in the block at the right side, it's the measurement unit. Okay, the measurement unit is the sensor I use. Okay, there is 16 pair of sensor capture the data and then will be uploaded into the FPGA, which is here is the sensor data memory. And then one sector from the measurement unit, it will be go to the main processing unit, which is in this case is the FPGA. Okay, the FPGA, the data will be pre-processing, then the algorithm will be executed. Okay, and once the FPGA processing done, the image will be displayed in the display unit. And my case here is just the normal monitor. Okay, output the final image with the enhanced quality. So for the implementation, as you can see here, my work is based on optical tomography, which is it can detect solid object okay inside the pipe here. Okay, and I'm using a 16 pair of infrared sensor. Okay, let me show this. This is a video actually. I can show you, and it's a real time. As you can see, when I move it inside the pipe, the display also move. This display is based on 60 frames per second. Okay. So as you can see, the display output here is there is still background effect or special effect because of the FBP. So from this video, still didn't apply the what we call it the thresholding value for the segmentation. Means once I apply the segmentation process, the blue or maybe like violet color, pink color will be eliminated, and only there is the red, more to the dark red color. Okay, okay, and then the benefit of the FPGA in the image reconstruction. Okay, just now I say the display of the image on the screen is just 60 frames per second, but in my work I able to process the data inside the FPGA starting from the image acquisition. Okay, for one run means one frame of image. Okay, it's very fast, and in the microsecond time. So the speed it's can reconstruct the image about almost 6,000 frames per second. So just the display for using the 60 frame, because of the limitation of the display, use the 60 frame per second. Okay, in the FPGA also it's a low latency, which means we can reduce the time between the input and output. Mean the processing is fast. Okay, and then also the FPGA can be customized. Okay, it's easy to customize. We can tailor the hardware to specific reconstruction need. Okay, and then I think this is the last one. Okay, the future direction of this work maybe for later work we can integrate this with AI. Just like what Dr. Hafiz from Unimed just this morning. Maybe we can enhance the reconstruction with the machine learning models. Okay, but the implementation should be in the FPGA because of the parallel processing to get the real time. Okay, and the other one is to increase the FPGA resources, because large FPGA resources will make the image more better. Okay, and also the complex design lah. Okay, and that's all, because my presentation today is just 10 page of slide. So I think we can go to the question. Okay, I stop the sharing first.
Okay, thank you very much, Mr. Rahman, for your presentation.
Okay, any question?
Okay, thank you very much, Mr. Rahman, for your presentation. We will now open the floor for question. Any question from the floor? There's a question here right now. I'm not sure whether you can understand or not. For now, what is the latest FPS from other researchers using FPGA?
You mean for the image reconstruction, right, Albert?
Yes, yes. Latest FPS. I believe that this question is directly from your superior.
Okay. So far, I didn't see any research for now. So in my work, so far I didn't see any research for the fastest one.
Okay, understood. I also agree with you with that. Okay, thank you very much, Mr. Rahman. Okay, we continue with the next presenter after this, and thank you very much for the presentation, Mr. Rahman.
Okay, thank you.
Okay, we'll take a break another 5 minutes before we'll start with the last presentation presenter, also a student, Mr. Dennis Hamid from the Air University. Okay, we'll start by around 3 o'clock, perhaps. Okay, thank you everyone. We hold for a break for 5 minutes. Thank you. Okay, we would like to welcome Mr. Dennis Hamid joining us right now. I believe he will need some time to prepare. For everyone information, the next we will have Mr. Danish Hamid from Air University, Pakistan, who will be presenting on enhancing recognition of human-object interaction from visual data using egocentric wearable cameras. Okay, whenever Mr. Dennis is ready, you can share your slide. If I'm not mistaken, right now, Pakistan is around 12 o'clock in the afternoon.
Bismillahirrahmanirrahim. Assalamu alaikum. My name is Danish, and I'm here to present my research work I'm doing here at Air University Islamabad. The title is A Novel Framework for Recognition of Human-Object Interaction from Visual Data, and it is being supervised by Dr. Manullah Yassin and Dr. Tisham Ulaq. The major research area is the computer vision, and under this major research area, the research pockets we have used in our research are object detection and recognition, human action recognition, deep learning for visual data, and human object interaction recognition. Mostly we will be focusing on HOI recognitions in videos, basically. So let's start with the basic idea. What human object interaction recognition is basically used in several kind of applications related to safety, security, and surveillance, as depicted in these diagrams or images here. So suppose we have a child standing near the pool, and we are watching that scene using a surveillance camera. We can detect the movements of the child, or whether the child will go near towards the pool or not, and we can make necessary actions. Similarly, if a thief comes to any shop or any organization, and if he or she have a gun in his or her hand, then we can detect that action as well for the security purposes, and so on and so forth. So, in human object interaction recognition is a very vast field of computer vision, and much research is going on in the around the globe on this particular aspect. And mainly, when we talk about human object interaction, we are talking about a triplet. That is the person, the human, which is performing the interaction, the object with which the person is performing the interaction, and the third verb, that which kind of work is being performed by the object, by the person with the object. For example, a person is holding a kettle and pouring tea from it into a cup, or a person is riding a horse, a child is eating an apple. So in HOI, we detect all these three things, like which human is performing the interaction, with which object he or she is performing that particular interaction, and of course lastly the overall interaction. So according to this, we can understand the scene in the particular input or image or a video. So our problem statement in our work, we have gathered all the limitations existing in the existing methods in which people have worked over the HOI recognition, and we have tried to overcome these limitations by using data from multi-model model sources, and proposed a framework which can do the desired task very efficiently. Here are our research objectives, which we initially decided. We will separately, because there are several methods available, in which two are very famous. That there are two types of methods. Number one is the single stage method, in which interactions are directly predicted from the input image or video. The second method is the two-stage method, in which they divided the task into the two steps. The first step is that first we identify and recognize the object with which the interaction is being performed, and then then we can classify the interaction related to that object only. This will squeeze our search domain, and due to this approach, we can increase our performance. But there is a problem with this two-stage method. In two-stage method, we have time complexity overhead as well. So there is a trade-off between these two methods. So we will try to achieve applying our framework on both of these methods, and get the analysis that what are the differences. So in first objective, we are giving a model which will detect and recognize images from recognize the object from images and videos using different type of visual information. The second one is based on the first objective, that if we are having the object information, then we can recognize the HOIs based on that information, along with the features of object interaction and detection. The third one is to use hand pose information from images, to extract hand pose information at first place from the images and videos, and then based on the features of those hand poses, we can detect our HOIs. Finally, by concluding, by mixing and fusion of these different visual data, we will decide a framework for a robust recognition of HOIs. So a lot of literature has been done on This, as I have already mentioned, that several research is being carried out on HOIs in our past, and so few are discussed here. These are the benchmark data sets which are used for HOI recognition. Among these, there are few very famous and widely used in the literature, that are VCOCO and HECODAT. These are very much applied in different searches in the past. But we used HOI 4D dataset as depicted in this particular table. That several limitations we have in other datasets which are being covered in HOI 4D data. This is a large scale dataset which is being published in 2022 in CVPR, and mostly the aim of this particular data set is to overcome the limitations of previously presented data sets. So that's why we choose this data set to be the part of our research. And there several methods have been developed initially for HOI detection and recognition. Initially, machine learning in early in 2010 to 2015, there are several handcrafted features made on different data sets to predict the HOIs, in which structural models, SVMs were used, multiple stage pipelines will be used. But mostly after the evolution of deep learning, most methods are using the deep learning techniques, in which common are CNNs. When we are trying to classify HOIs using images, CNN is the right choice. And then we have furthermore GANs are also used to reproduce the data set, and the quite famous two methods which are being used nowadays are transformer based techniques and graph convolutional network techniques, which are being widely used. But the problem is with the deep learning approaches is, again, we need a large scale data set, a very well established data set we need it, and of course the problem of computational overhead and your time complexity is very relatively high. So in real time systems, we cannot use such kind of models, because where latency is important, then deep learning techniques based models for HOI recognition usually fails. So let's directly goes towards the methodology we adopted for HOI recognition. This is the first methodology for the first objective we have designed. What we did is we have chosen the HOI 4D dataset, and this is basically a streamed video dataset in which we have more than 4,000 video sequences of the same length. But this data is not annotated for object detection and recognition. So what we did is we converted this video data set into frames, and we collected the samples from each video in a way that we collected few frames from the start of the video, few frames from the middle of the video, and few frames from the end of the video. The reason behind this approach is that we want to capture the object of concern, because when a hand interacts with the object, then we can get the direction that this particular object is our concerned one. Because in complex scenarios, in complex scenario videos sequences, there are multiple objects which are considered in our data set, but there is only one object which is the concern in particular one video. So that's why we have tried to get all the sides of the videos to get samples, and we have manually annotated these samples to be exact, we have annotated 7,536 samples, manually annotated them, and then we apply YOLO V8 on that and get the results. That was our first objective. The second objective is for directly getting the we have two methods with objective HOI recognition. If we want to get HOI recognition, then we can use with object information, that is our two-stage method, that we get the object label from here, because in this data set we have 54 different HOI interactions corresponding to the 16 different objects. So what we did is in the first diagram we can see here, we first detected the object and recognized it, and then based on this information we get features from the video, and we extracted features using I3D, and we recognize the HOIs. So in that case we have at max against one object there are not more than 6 interactions. So as we have limited interaction classes, so it is our hypothesis that if we have less classes then it will perform well. Similarly, we have also investigated it using without using that object information. So in this we just get the features from the bare video using I3D, and we have directly classified those 54 classes and get the results. This is the actual thing on which we have our publication as well. In this, we have just converted the video, a single video, and extracted and converted it into frames, and we have extracted 3D hand joint information. These are 21 landmarks of hand joints, and we have extracted these using nano layer, and we have extracted features from these hand joints using statistical attributes, and we have got the results, and this is being published in Future of Internet. And the reason we have used this because if we do get good results using hand poses, then we can use it in real-time systems, because there is no deep learning involved here. We have just handcrafted these features using statistical attributes, and we just apply a simple classifier at the end. So this is relatively fast than the other methods. And finally, we fused these two methods. One is from the I3D method. We first identify the objects, and using I3D we have collected the features for interaction and recognize it, and the fusion it with the hand pose data. So how we perform the fusion? We perform the fusion at the feature level. We have extracted features for this extracted the flow and RGB features both from I3D, and we aggregated them using a pooling technique, and we concatenated these features with the features we have collected from the hand poses and achieved the results. And we have seen in the results that they are significantly high. At HOI 4D dataset, we get the results like 94% F1 score for two-stage method, and for single-stage method we have got 83% results for a single-stage method. So method of analysis, we have validation scheme of 5 cross-fold. We have applied on our all experimentation. We applied a 5 cross-fold validation, and we mainly use the F1 score as our evaluation metric. The results I've already discussed, because these slides are just before 2 months before, and now we have the results. For the best results we have achieved till now are 94% for two-stage method. Of course, there is a time complexity overhead in this technique. So also we have achieved 83% results in single stage method, in which we have I'm talking about the final fused framework, in which we perform frame level in which we perform feature level fusion with of hand pose features along with the RGB and optical flow features, and we have concluded it like this. That's all from my side. Thank you very much. Any questions? If you have any questions, please you can ask.
Okay, thank you very much, Mr. Danish, for the fascinating presentation. And now we would like to open the floor for any question from the fellow audience. Seems very interesting to everyone. We have 5 minutes for the session. Any question for the fellow audience? Okay, I believe that's a question. Everyone is in full capacity of understanding every presentation. Thank you very much, Mr. Dennis. Yeah, for continue our program for the closing ceremony. Now we have come to the closing ceremony. I would like to invite the Symposium Chair to give the closing remark. Please welcome Symposium Chair, Associate Professor Siti Zarina Muji, give his speech.
Sorry, your voice is not coming clearly to me. Can you please repeat?
It's okay, Doctor. It's okay, Mr. Danish. That
Yes.
the question. There's no questions for you. Seems that everyone is in good understanding of your presentation.
Thank you. Thank you very much.
To continue, we'd like to invite the Symposium Chair to make a closing remarks. Without further any delay, I would like to invite Associate Professor IR Siti Zarina Muji.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And good afternoon, ladies and gentlemen, esteemed speakers, participations, and distinguished guests. As we draw the Computational Signal Image Processing and Intelligence Symposium 2024 to a close, I'm filled with a sense of pride and gratitude. Over the course of this symposium, we have explored the theme Moving Forward Computer Vision and Artificial Intelligence through a series of insightful presentations, thought-provoking discussions, and collaborative exchanges. Each of these presentations has provided us with a glimpse into the future of computer vision and AI, showcasing the groundbreaking work happening in these fields and the opportunities they presents for innovation. I want to take a moment to express my heartfelt thanks to our participants from Malaysia and Pakistan, or maybe from other countries, and the dedicated committee members from CSII, CVSP, DSIP, and MyCT research groups. Your hard work, dedication, and collaboration made this event possible. As we move forward, let us continue to build upon the insight gained here and let this symposium be a catalyst for new ideas and partnerships. Together, we are shaping the future of technology and driving forward the possibilities of computer vision and artificial intelligence. Thank you all, and I look forward to what lies ahead. Thank you.
Okay, thank you for your closing remarks, Dr. Siti Zarina. We have reached to the conclusion of today's symposium. On behalf of the organizing committee, I would like to thank to all our speakers, participants, and everyone who contributed to making this symposium a success. And we'd like to apologize for any shortcoming from our side. Before we request for the final photo session, I'd like to remind everyone in joining us for today to fill the attendance form so that we can generate a certificate, I believe, for your participation. Okay, once again, thank you everyone, and we hope that to see everyone in good shape. Okay, before we close our session, I'd like to everyone to open your video cam, sorry. Video cam, okay. Okay, another 5 minutes, 5 seconds perhaps.
Kita tak on. Kita tak ada disconnect. Maka kat sini boleh ambil.
Okay. We'll take your pictures in 3.
Semua orang ambil kan?
Okay. On count to 1. 3, 2, 1. Get another one with the biggest smile of your life. Smile. 3, 2, 1. Okay, once again, thank you very much. We hope to see you at a future event. Have a great evening ahead, and thank you very much. Bye. Assalamualaikum warahmatullahi wabarakatuh.